generated. And today I'm going to start by reviewing some of the material we talked about in kind of a haste at the end of the last lecture, and then give you a new kind of interpretation of this generation of the cat states based on what you by now should know very well, which is the interference of two alternative paths. Okay, and then we're going to talk about some important properties of the coherent state, and then in the end we're going to look at the Wigner distribution, both the coherent state and the Wigner cat states, and I'll show you how these exactly how we can visualize these interferences existing in the coherent in the cat states. Okay, so just a review of what we talked about last time. We talked about the dispersive interaction and some usage for it. So the picture is this: we have a three-level atom, and then we have the excited and the ground state, and some state that is very far off resonance with these two, and it's labeled F. Okay, so we take, as always, the transition frequency between the excited and the ground state to be omega naught, and then we have some cavity which has a frequency of omega c, which gives you a detuning of this delta factor. And then we also have cavities which are resonant with the G and F transition, and that resonance frequency is omega r. So there are two kinds of operations in the preparation of cat states from atomic states. First one, we need the resonant pi/2 pulse, and this is called a Ramsey zone, if you remember. Okay. These are this, and over here, this. So what this does is it realizes the Hadamard gate, which is a rotation in the Bloch sphere, on the Bloch sphere. Okay, so it takes G to an even superposition of G and F, and takes F to an odd superposition. Okay. So this is what the pi/2 resonant pulse does. And then we have our off-resonant dispersive interaction, and by controlling chi t to pi, okay, that was this detuning factor here. So we're essentially coupling the cavity to these two states, but the excited state is not populated in our setup. Okay, so only the ground state gets acted upon, and the state with F, you can couple to a coherent state of the cavity. Nothing happens to this. Okay, it just gets carried over. Whereas for the ground state, there's a minus sign given to the coherent state. Okay. So this is the sketch of the experimental setup. So we have some oven that gives us these atoms, okay, and we prepare these atoms, okay, using some black box which we will not be concerned with here. Okay. We prepare them into the ground state, the G state, and then we subject them to this pi/2 resonant pulse, so they end up in this linear superposition of the ground and the F state. Okay. And then we have this dispersive interaction cavity with populated with a coherent state in it. So afterward we get this, and then of course if we do another resonant pulse, then we split these fields, but I'm not going to write them down. And so in the end, over here we're going to subject the atomic beam to some kind of excitation to determine whether the atoms are in the F or G state. Okay. So that kind of ionization is a determination of whether, which of these atomic states the atom is in, and therefore it projects the field onto the so-called cat states. Okay. So here's another way to represent this process. Okay, we can think about these Ramsey zones as being sort of beam splitters that creates alternating paths. Okay, so we start with the ground state. It passes through the first Ramsey zone and it gets split into two states, right? The G and the F. So we create two alternative paths. Okay, and then over here we couple this to the alpha, to the coherent state. Okay, and then for the omega c, this is just a propagation. And the propagation is such that it leaves F alpha unchanged, whereas it gives this a minus alpha. And then over here, we subject it to another Ramsey zone, which is another kind of splitting for the atomic states. Okay, And then in the end, we're going to look at the things projected onto F or G, okay, which picks up either these two or these two. Right? And if we trace things back, we can see that in the projected picture, okay, for instance, these two states, okay, we can say that the interference which is present in the Schrödinger cat states is coming from these states being from two interfering alternatives, right? And we know it from quantum mechanics if they can be from two alternatives, then those two alternatives are going to interfere. So the Schrödinger cat state, the generation of the Schrödinger cat state comes from interference ultimately. So and today we're going to try to develop a mathematical description of this kind of interference using the Wigner distribution. Okay. So it might be a bit mathematical today's lecture, but if you just follow with me, I think it's still understandable. Yeah. So now, before we talk about the Wigner distribution and the cat states, I'm going to review for you some properties of the coherent state that might not have been emphasized before. So the coherent state. So what do we need? What properties do we need of the coherent state in order to study the cat states? Think about the cat states are something like a superposition of this. This is called the even cat state. Okay. And this is clearly not normalized. So then this is called the odd cat state. The first thing we need to do is to normalize them. And in normalizing them, we need to think about the overlap between alpha and minus alpha. Right. So let's think about. By now you should be familiar with the formula for the coherent state. Right? So let's think about two coherent states expanded onto the number of states, and let's find their overlap. Okay. So another coherent state may be given by beta. Let me use M over here. Okay, so now if I turn this into the bra and then I take the inner product of these two, what happens is these M states is going to see the N states and it's going to take out a delta Mn, right, a Kronecker delta function. And that Kronecker delta function is going to remove one of these summations, right? So explicitly we get that. So beta L is okay, we have this exponential factor out in the front, and then there's a summation over m and a summation over n, square root of n factorial m factorial. Okay, and the beta is what gets conjugated because that turns into the bra. So beta conjugate m alpha n, okay, and then a inner product of m and n, which gives you a Kronecker delta function. This Kronecker delta removes one of these summations, so we're left with a matched term of m and n. So what we get is e to the minus and you recognize this as an exponential. Okay. So the the overlap between two coherent states can be written as some factor like this. Okay, multiplying a phase factor, which is e to the phase. So now we can rearrange some terms. We can take out a magnitude thing, and also take out a phase factor. So what we end up with is something like, so the overlap between beta and alpha is e to the okay. So this is just some mathematical manipulation that you can go through on your own. But what's important here is that, now notice this is completely, the exponent over here is completely an imaginary thing, whereas this is a real thing. So we separated this into polar form. Okay. And now for the special case that we're interested in, this alpha minus alpha type of thing. Suppose that alpha is real for now, then we get rid of this. We get rid of this phase factor. Okay, and then over here we just have something like e to the minus alpha. Okay, so we have that this is equal to e to the minus alpha squared. And the phase factor, even if this was not real, the phase factor would just come out to be not important in terms of normalization, right? So if we think about normalizing the coherent states, so let me say that there is a normalization factor here, and the normalization factor here, E for even, O for odd. Okay, we will get something like, let's say for the even state, we have alpha plus minus alpha minus alpha, okay, plus 2 times minus alpha, where we're not concerned about the phase. Okay. So if we plug these into here, we find that so two coherent states are give you 1. Right? So these both give you 1, and then this is 2 times e to the minus alpha squared. So their overlap produces this kind of a normalization constant, which is 2 plus 2 e to the minus alpha squared. Okay. So I think you probably recognize this factor from your homework, right? Okay. This comes out when you comes out when you consider normalizing two Gaussian packets that have some overlap. And the reason is that the coherent state, when you represent it onto this alpha plane, the alpha thing for the coherent state, this is a complex number, and we can represent the coherent state onto its real and imaginary parts. When you represent this onto the alpha plane, you'll find that the coherent state is actually just a Gaussian packet. So it shouldn't come as a surprise that the normalization here looks like the normalization for two Gaussian packets. And we'll show this explicitly later when we look at the Wigner distribution. Okay. So this is one thing we need to know about coherent states, which is their overlap. Okay. So suppose that alpha and beta are not separated enough, then we see that they might have some significant overlap. So it tells you that two coherent states are not orthogonal. So when we try to, for number states, we know that two number states are orthonormal to each other. So we can resolve the identity by summing over all of the number states. But if we try to resolve the identity as such, okay, suppose I say the identity, is it equal to the summation over these outer products of coherent states? And then of course the alpha is a complex number, so we're essentially integrating over the complex plane here. So is this equal? Okay. So let's find this out. So for that we will do exactly the same thing over there. So for this alpha I'm going to use the index n, and for this alpha I'm going to use the index m. Right. So the outer product looks like summation of m and n. Okay. Again we have this m factorial, n factorial thing. Okay. And then this is alpha conjugate to the m, alpha to the m power m, n. Okay. We have an integral. Okay, so d squared alpha, this is like, if you think about the complex plane, okay, you can turn this into an integral over the real part of alpha and an integral over the imaginary part of alpha. So now what we're going to do is we're going to turn alpha into polar form, okay, by writing alpha as r e to the I theta, okay, which means that alpha conjugate is equal to r e to the minus I theta, and r and theta are both real, okay. So now this integral turns, all these things are independent of alphas. So let me take the m and n out. So we have a summation on the outside. M factorial n.
What happened to your exponential factor outside?
Oh, sorry, I forgot to write. So the exponential factor is going to be e to the minus alpha squared. Because we have e to the minus alpha squared over 2 for both terms, right? So that's what it is. And e to the minus alpha, oh, it cannot be outside of the integral, it must be inside because it's dependent on alpha. So let me write it here. Okay. E to the minus alpha squared, the polar form turns into e to the minus r squared, right? So we have an integral over r, which is going to run from, and you have this differential element r dr, okay? And then we have e to the minus r squared coming from the e to the minus alpha squared thing. And then we have r to the m's, r to the n, and then an angular integral e theta. Okay. This is e to the I n theta, e to the minus I m theta. Okay. So you notice that this will give you 2 pi delta and n. So this gives you a primary delta over here. So let me erase some stuff. Let's see. Okay, maybe I can erase it. Okay. So over there, the angular integral allows us to write a 2 pi delta mn here. Okay, and this is going to again remove one of these summations for us. Okay, and notice that now we're in the comedian form of n, which is like resolving the identity onto the number stage where we have some extra terms. Okay, so now what we get is this going from 0 to infinity, square root of just n factorial now. And 2 pi. Okay. And then the radial integral, which is dr times e to the minus r squared, r to the 2n power. Okay? Yeah. Everybody is okay with this? Okay. So now, notice that this is conveniently, we can do a convenient change of variables here, changing r to r squared. Okay, so rdr gives you 1/2 the r squared, and then what's left is e to the minus r squared to the nth power, right? So what we get is that this is equal to summation over n, and this 1/2 is going to cancel with 2, so we have a pi. Okay, and we have 1 over n factorial, 0 to infinity. Let me use x for r squared. So dx e to the minus x, x to the nth power. And so what is this? This is just n factorial, right? From the gamma function. Okay, so this is just n factorial, which cancels with this. And we have over here the identity resolved onto the number basis. Okay. So roughly you can say this is equal to I pi. So to correctly resolve the identity onto the coherent state, what we need is that 1 over pi alpha. So this is the corresponding resolution of the identity onto coherent state. And the 1 over pi factor comes from the different coherent states being not linearly independent. They have some overlap, which we have shown. Alright? So that's what we needed to review about the coherent state. And then now let me move on to Wigner distribution. And then we'll come back. Remember the coherent state, we found the coherent state in 2 contexts, right? So we studied the harmonic oscillator, and we said that there were these creation and annihilation operators, and the coherent state there we derived by saying that it is an eigenstate of the annihilation operator. And then afterwards, we also found that we can construct the coherent state for the classical fields, right? When we quantize them. And we also showed you that the coherent state evolves in time as with a classical harmonic oscillator, right? So previously I showed you this so-called phase space picture of the coherent state. Today we're going to derive kind of rigorously how you get this phase space picture. So the phase space picture was this. I claim that when I represent the coherent state onto this alpha plane, complex alpha plane, then taking this to be the real part of alpha, this to be the imaginary part of alpha. Okay? So now I can write the coherent state as something like this. It's a small circle, and the circle base, the spread of the circle is determined by the uncertainty principle. And for coherent state, we have a minimum uncertainty. And then the radius, the kind of radius here is given by the magnitude of alpha. Okay. So now, this is actually just the Wigner distribution of the coherent state. And this little patch over here, as you'll find out, is actually a Gaussian function. So we basically take the significant part of the Gaussian peak, and we represent it like this. Okay. So today we're going to show you this, and for that we need the Wigner distribution. Are there any questions about what I talked about so far? Okay, no?
You want to mention something about when we overcomplete the opposite at that resolution.
Yes.
Overcomplete.
The reason that they're overcomplete is what I've erased here, right? They have overlap. Whereas 2 number states, if we were doing this kind of resolution, the 2 number states which are orthonormal to each other, they don't have this overcompleteness. So, Wigner distribution. So in classical statistical physics, there's something called a phase space description, and it has to do with the classical probability of the state being in a certain spread, a certain profile in the phase space. So the phase space is something like if you have this single variable that is x and its momentum p. So you represent the state onto this space. And for a particle with some possible spread in x and p due to classical uncertainties, which means that you don't know enough information, you don't have enough information about the particle. Okay, then the phase space picture of the particle might be this. Okay? And the distribution function is determined by statistical physics. So the Wigner distribution tries to construct from the wave function and the density matrix for an ensemble or a single particle something similar to this. And it's very similar to this in several ways, which we will show you right now. So the Wigner distribution is this. If we have some density operator rho, okay, and the density operator rho, the Wigner function of this density operator is given by, I'm going to use, so let me use the standard notation to denote this by Q instead of X. So Q and P is equal to 1 over 2 pi h bar minus infinity to infinity dx. So this is defined as the Wigner distribution. So now why is this, how is this related to classical distribution? And also why is this important? So some properties of the Wigner distribution are already apparent from this, from its definition. So first of all, consider taking a conjugate of this. Okay? If I take the conjugate of this,
Rho hat is a density operator.
right, density operator. And we know that the rho hat is what? It's Hermitian, right? Okay, so since this is Hermitian, so this factor just goes into this, and then we have e to the minus ipx. So now if I switch x to minus x, we find that these two are equal. Right? So when something conjugate is equal to itself, this thing must be real. Right? So unlike the elements of the density operator or the wave function itself, the Wigner distribution is a real function. So real functions, we can make connection between real functions and classical physics more easily than we can between complex functions. Okay, because in classical physics, most distributions that we know must be real. Okay? But then to really make this into a classical distribution in the probability sense, we need to have the Wigner function being all positive, right? Because there's no negative probability. But for some cases, that is not the case, which we will show later. For the coherent state, however, the Wigner distribution is completely positive. Okay, so it can be interpreted as some kind of a classical probability distribution. So and then there's also another interesting property of the Wigner function, which is if I integrate the Wigner function over the variable p, I recover the magnitude squared of the wave function. Okay? And this kind of resembles the classical distribution, where if you have a joint probability distribution of two variables, q and p, okay, you integrate over one of them, you get the probability distribution of the other. Let me show you that. So consider the special case in which rho is the density operator for pure state. Okay? So we have some psi. Right? Now, this gets acted on by these bra and cat, and it turns into just a wave function. This one's got a complex conjugate. So we have W of psi for this, the Wigner distribution for this thing is 1 over 2 pi h bar. Psi of and then we have that phase factor. Okay. So, yeah. Okay. So what happens now is that the x integral is going to give you a delta function, right? And we can use that to remove the remove those these x's. And basically, if I integrate now I integrate this from minus infinity to infinity dp on this side. Okay. This is equal to, let me write it over here, because we're running out of space. 1 over 2 pi h bar. I leave the x integral on the outside. And, oh, sorry, I forgot to. Okay, p and x have a dimension, right? So that's not correct. We need to divide by h bar here. Okay, so this integral gives you, well, just 2 pi h bar, right? Which cancels with this over here, and it leaves you with a delta x. Okay, and this delta x is going to remove that x integral over here, replacing x with 0. So we find that this is just equal to the magnitude squared of psi 2. Okay. We know that we have, so far we have interpreted this wave function, the magnitude square of the wave function, as the probability distribution for the observable Q, right? So you see that integrating the Wigner distribution over its conjugate, the other variable, gives you the probability distribution for this variable. Okay. Now, we can equally well show that the Wigner distribution, when integrated over Q, it gives you the probability distribution, which is the wave function in the momentum space, magnitude squared. Okay. So for that we need a symmetric definition of the Wigner distribution. So we can show that by thinking about this. Okay. So now if I integrated this thing over OQ, what I'm going to get? I'm going to get 1 due to normalization of the wave function. Right? So dq psi q squared. This is equal to 1, and according to that equation over there, we get this is equal to dq dp, the Wigner distribution, q and p. Correct? Okay. So if I turn this 1 into this, psi of p squared. It must mean that dp minus infinity to infinity dq. Okay, so we can match terms and say that phi of p squared is equal to integral over q of the Wigner function. Okay, correct? Okay. So the Wigner function is some kind of a joint probability density function between the variables q and p. But now, if you look at the definition of the Wigner function, which I have erased, sorry. Okay, so I mean, what's very strikingly absurd about this definition? Think about these. You get this plus 1/2 x and minus 1/2 x. What are they for? Why do we have this? First of all, you should remember that in quantum mechanics, although these things look like classical distribution functions, should we ever get a classical joint distribution function for q and p? No, right? Because there's something called the uncertainty principle, which forbids us to know both the phi of p, which is the probability distribution function for this, and also its psi of q. Okay. So these things we should not know simultaneously. And the Wigner distribution respects this in the sense that, okay, you can construct the magnitude squared of this function from the Wigner distribution. Also, you can construct the magnitude squared of this function from the Wigner distribution. But to go from, remember these two are related by Fourier transform. Okay? To go from
How do you get the second line, the left-hand side? How do you get this?
left-hand side, second like this.
Yeah.